More than 2.3 billion people are already living in dry. Israel is the only country where the desert is becoming smaller.
They drilled into a desert and accidentally discovered something that should not exist. What they found 2,300 feet underground completely broke every rule of modern science. American researchers could not believe what they were seeing, because buried beneath one of the most hostile places on Earth was a secret that had been sitting there for 40,000 years, just waiting to be found.
This chunk of land has the potential of keeping us in the front line of innovation.
And when Israel figured out what to do with it, they did not just solve their own food crisis, they accidentally solved the world. Nobody saw this coming. Nobody was prepared for what happened next. The Negev desert covers roughly 60% of Israel's total land area. That is a significant portion of a country that is already small by most standards, and yet for most of human history, that land was considered almost entirely useless. Not because nobody tried to do anything with it, but because the most basic requirement for any kind of productive land simply was not there. Water. The Negev receives rainfall maybe twice a year. In some years it gets less than Death Valley in California, which is widely considered one of the driest places in the United States. Summer temperatures regularly climb above 113 degrees Fahrenheit. The ground is a mix of limestone, dust, and compacted rock that bakes under a sun that rarely takes a break. For centuries, the assumption was straightforward. You cannot farm what you cannot water, and you cannot water what receives almost no rain. So the land sat there, largely untouched, while the rest of the country developed around it. That started to change in 1973 when a geologist named Eliyahu Raz was part of a team conducting a survey of underground rock formations in the region. Geological surveys of this kind are fairly routine. Teams drill into the ground to study what is down there, to map out the layers of rock and sediment, to look for anything that might be scientifically or economically useful. Most of the time, these surveys confirm what everyone already expects. In the case of the Negev, the expectation was rock, more rock, and not much else. The team drilled down through approximately 2,300 feet of solid sandstone. That is a significant depth, well below the surface layers where groundwater might normally collect after rainfall. At that point, they hit something that nobody on the team had anticipated. Water. Not a trickle, not a damp patch in the rock, but an actual body of water sitting under enormous pressure that had been building for a very long time. When the drill created an opening, the water did not need to be pumped. It shot upward entirely on its own, forced to the surface by the underground pressure that had been holding it in place. A self-flowing artesian well, powered by nothing more than the weight and geology of the earth above it. What the team had found was a section of what geologists call the Nubian Sandstone Aquifer System, one of the largest underground water reserves on the planet. The aquifer, stretches beneath 4 countries: Egypt, Libya, Chad, and Sudan. In total, it covers over 770,000 square miles and holds an estimated 120,000 cubic miles of water. To put that in some kind of perspective, that is enough water to fill Lake Superior roughly 40 times over. The Israeli section sits at the very northern tip of this system, a fragment of this vast underground reservoir that extends beneath parts of the Negev and into the Sinai Peninsula. The water that came up from that depth had not been anywhere near the surface for a very long time. Geologists refer to it as fossil water, and the name is fairly literal. This water fell as rain tens of thousands of years ago, during a period when the climate in that part of the world looked completely different from how it looks today. During the last ice age, somewhere between 20,000 and 40,000 years ago, the Sahara was not a desert. It was a grassland, covered in vegetation, fed by regular rainfall. As the climate shifted and the region dried out, that rainwater seeped down through porous rock and became trapped in the sandstone far below the surface. It has been sitting there ever since in complete darkness under steadily increasing pressure, completely disconnected from the modern water cycle above. The discovery made headlines. Israel had found an ocean beneath the desert. The question of what to do with it, however, turned out to be far more complicated than anyone initially expected. The first problem was temperature. The deeper you go into the earth, the hotter things get. This is because of geothermal energy, the heat generated by the Earth's core and by the natural radioactive decay of minerals in the rock. At 2,300 feet below the surface, that heat keeps the water at a constant temperature of between 99 and 104 degrees Fahrenheit. That is roughly the temperature of a human body running a fever. It is warm enough to be immediately uncomfortable and, more importantly, completely unsuitable for any conventional agricultural use. You cannot irrigate crops with hot water. The thermal stress alone would damage most plants before the water had even soaked into the soil. And in a desert environment where the air temperature is already pushing toward dangerous highs in the summer, adding hot water to the equation does not help anything. The second problem was salt. Water that has been sitting inside porous rock for tens of thousands of years does not stay chemically neutral. Over that kind of timescale, it slowly dissolves minerals out of the surrounding rock, picking up salts and other compounds along the way. The water coming up from the Nubian aquifer had a salinity of around 3,000 parts per million. For reference, seawater sits at roughly 35,000 parts per million, so this was not seawater. It was not even close to seawater, but it was salty enough to cause serious problems for agriculture. To test the water's viability, engineers set up a series of experimental plots and irrigated them using water drawn directly from the aquifer. The results came back quickly, and they were not encouraging. Within 72 hours, the vegetable plants in those plots were already showing visible signs of salt stress. Leaves yellowed. Growth slowed noticeably. The plants were not dying immediately, but they were clearly struggling. Within 2 weeks, the majority of them were dead. The salt in the water was drawing moisture out of the plant cells through a process called osmotic stress, essentially dehydrating the plants from the inside even while water was being applied to their roots. The Agricultural Ministry reviewed the findings and reached a logical conclusion. The water from the aquifer was not suitable for irrigation. It was not suitable for drinking. It was too hot, too salty, and too far removed from anything that conventional farming could work with. The recommendation was to cap the well and move on. But not everyone was ready to accept that conclusion. One researcher, looking at the data from a slightly different angle, asked a question that reframed the entire situation. Instead of asking what the water could not support, the question became, somewhere in the world, in rivers and estuaries and coastal waters, there are species that already live in conditions very similar to this: hot water, brackish water, fluctuating salinity. What lives there, and could it live here? The answer was sitting in rivers 5,000 miles away in Australia and across parts of Africa and Southeast Asia. And it would eventually change not just what the Negev produced, but how the world thinks about what a desert is actually capable of. The fish that researchers settled on was the barramundi, a species with a prehistoric appearance and a biological profile that seemed almost designed for the conditions found in the Negev aquifer. Barramundi are native to the coastal rivers of Australia and parts of Southeast Asia, and they have been caught and eaten by humans for at least 40,000 years, making them one of the longest continuously harvested food fish on record. They are not a new discovery, they are not an exotic curiosity. They are a well-understood species with a long history of human use, and their biology turned out to be precisely what the situation required. In their natural habitat, barramundi do not live in a single, stable environment. They move. They spawn in salt water, then migrate into freshwater rivers as they grow, and their bodies are built to handle the transition between the two. This means they can tolerate a wide range of salinity levels without significant stress, which immediately made them relevant to a situation involving brackish water sitting at 3,000 parts per million. But the more important factor was temperature. Barramundi are a tropical species. They thrive in water that sits between roughly 79 and 93 degrees Fahrenheit. Below that range, their metabolism slows, their immune systems weaken, and their growth stalls. Drop the MIG. Temperature low enough, and they die. The water coming out of the Negev aquifer, heated by geothermal energy to between 99 and 104 degrees Fahrenheit, sat right at the upper edge of that comfortable range, and with minor management, it could be kept well within it. This is worth pausing on for a moment because the implications are significant. Barramundi are notoriously difficult to farm in most parts of Europe and North America precisely because of the temperature requirement. During winter months, outdoor water temperatures in those regions drop well below the survival threshold for tropical fish. Farmers who want to raise barramundi in those climates have no choice but to build and operate heating systems, and those systems are expensive in ways that quickly become financially unsustainable. Fish farmers in Northern Europe can spend tens of thousands of pounds or euros every year on heating infrastructure alone, burning fossil fuels throughout 6-month winters just to maintain water, temperatures that barramundi need to survive. That cost gets passed on through the supply chain and ends up reflected in the price consumers pay. Barramundi farmed in cold climates is an expensive product because cold climates are the wrong place to raise it. In the Negev, there are no heating costs. The geothermal energy that made the water useless for drinking and crop irrigation solved the heating problem entirely, at no cost, without any infrastructure, and without burning a single unit of fuel. Winter nights in the Negev can push down to around 41 degrees Fahrenheit at the surface, which would be fatal to tropical fish in an outdoor pond drawing from surface water. But the water being pumped up from 2,300 feet below ground arrives at the surface at a constant 100 degrees, regardless of what the air temperature is doing above. The fish live effectively in a permanent summer, the season that is hardest and most expensive to replicate in conventional fish farming simply does not exist for them. Alongside barramundi, Israeli researchers identified 2 additional species as strong candidates for the system. Tilapia, a hardy freshwater fish with a broad tolerance for varying water conditions, can handle salinity levels up to around 15,000 parts per million, which is 5 times higher than the concentration found in the aquifer water. It is a resilient species that has been farmed commercially across Africa, Asia, and the Americas for decades, and its adaptability made it well suited to conditions that would challenge more sensitive fish. The second candidate was European sea bass, a species that naturally migrates between freshwater and marine environments during its life cycle and is therefore biologically accustomed to handling changes in salinity. Both species adapted well to the aquifer water, and in the early 2000s, farms in the Negev began building the infrastructure to raise all 3 at scale. Kibbutz Mashabe Sadeh and Aquatech Fisheries were among the first operations to commit seriously to the model. They constructed large earthen ponds and concrete tanks across sections of the desert, drilled additional wells to increase the flow of water from the aquifer, and installed aeration systems to keep oxygen levels in the ponds at levels suitable for dense fish populations. The fish were introduced, and the results were immediate. The species adapted without any apparent difficulty, because from their perspective the environment was not unusual. It was warm, it was brackish, it was chemically similar to the estuaries and river mouths they had evolved to live in. Within months, the Negev had become one of the more productive fish farming zones in Israel. Kibbutz Mashabe Sad expanded its ponds to cover 30 acres. Aquatech Fisheries grew to 49 acres with an annual production exceeding 800 tons of fish. But scaling up introduced a problem that every fish farmer eventually encounters, regardless of where they are operating or what species. They are raising waste. Fish produce ammonia as a byproduct of their metabolism. It is excreted through their gills and released into the water continuously. In a small pond with a modest number of fish, the natural biological processes in the water can manage that ammonia well enough. But in a large commercial operation with hundreds of thousands of fish consuming significant quantities of feed every day, ammonia levels can rise to dangerous concentrations very quickly. At just 2 parts per million, ammonia begins to burn the delicate tissue of fish gills, impairing their ability to extract oxygen from the water. At higher concentrations, it causes neurological damage and suppresses the immune response, leaving fish vulnerable to disease and infection. Bacteria in the water convert ammonia into nitrite, which carries its own toxicity, and then into nitrate, which is less immediately dangerous, but still harmful at elevated levels. The overall effect is that the water in a heavily stocked pond becomes progressively more hostile to the animals living in it. Left unmanaged, the fish would essentially poison themselves. Traditional fish farming addresses this through one of 2 approaches. The first is mechanical and biological filtration, which involves pumping water through sand filters, biological filter beds populated with beneficial bacteria that break down ammonia, and sometimes ultraviolet sterilization systems that reduce bacterial loads. These systems work, but they are expensive to build and expensive to run. The pumps and aeration equipment alone can consume enough electricity to power dozens of homes. Operating costs for filtration and aeration at a commercial scale can exceed $30,000 to $50,000 annually. The second approach, used primarily by ocean-based fish farms in countries like Norway, Chile, and Scotland, is to flush the waste-laden water directly into the sea, where it dilutes across a large volume of water. This solves the immediate problem for the fish farmer, but the environmental consequences are considerable. Excess nitrogen and phosphorus from fish waste fuel algae blooms that can strip oxygen from the water and damage marine ecosystems over time. In the Negev, neither option made any practical sense. Filtration was too costly to justify in an operation that had access to essentially free water. Dumping was impossible because there was no ocean, and in a desert environment, water was far too scarce and valuable to simply discard. The farms were facing a genuine operational problem with no obvious solution. The breakthrough came from a shift in perspective, and it's the kind of shift that seems obvious in hindsight, but was not at all obvious at the time. Ammonia is toxic to fish. That much is straightforward and well established. But ammonia is also nitrogen, and nitrogen is the single most valuable nutrient in agriculture. Farmers around the world spend over $100 billion every year purchasing synthetic nitrogen, fertilizer, most of which is produced through the Haber-Bosch process, an industrial chemical reaction that combines nitrogen from the atmosphere with hydrogen derived from natural gas. The Haber-Bosch process is one of the most energy-intensive industrial operations in existence. It accounts for roughly 2% of the entire world's energy consumption. The fertilizer it produces is effective, but it comes with a significant financial and environmental cost. The fish in the Negev ponds were producing nitrogen continuously and for free. Not synthetic nitrogen, but organic nitrogen in forms that plants can absorb directly. The engineers working on the problem realized that what they had been treating as a waste management crisis was actually a resource that had not yet been connected to the right destination. Instead of filtering the water or discarding it, they built irrigation pipelines running directly from the fish ponds to agricultural fields planted nearby. The water leaving, the fish tanks had released some of its geothermal heat into the pond environment and arrived at the fields at a lower, more manageable temperature. It flowed into the root zones of olive trees and date palms, two species that are native to the Mediterranean and Middle East and have evolved to handle naturally saline soils. The trees absorbed the nitrogen, phosphorus, and potassium present in the fish waste. The soil acted as a living biological filter, with bacteria continuing to process ammonia into less harmful compounds, and the water seeped gradually back toward the aquifer, cleaner than it had been when it arrived. The first trials were conducted carefully, with researchers monitoring soil salt levels closely, expecting the brackish water to cause the same kind of damage it had caused on the vegetable plots years earlier. That damage never materialized. Olive trees and date palms can handle salinity concentrations up to around 5,000 parts per million. The aquifer water sat at 3,000. Not only did the trees survive, they grew faster than expected. Fruit yields on the experimental plots at Mashabe Said increased by between 15 and 20%. The fish waste, it turned out, released its nutrients gradually rather than all at once, which is exactly how plants prefer to receive them. Synthetic fertilizer dumps a large quantity of nitrogen into the soil in a single application, and plants can only absorb so much at a time. The excess runs off into groundwater or nearby waterways, carrying pollution with it. Organic waste breaks down slowly, delivering a steady supply of nutrients over weeks, which matches the pace at which plants can actually use them. The salt that everyone had assumed would eventually ruin the soil turned out to be manageable in the longer term as well. Monitoring over several years revealed that salt levels in the irrigated fields remained stable and in some areas actually declined. Date palms and olive trees absorb salt through their root systems and concentrate it in older leaves, which fall during routine pruning and are removed from the field. The trees were not merely tolerating the brackish water, they were actively reducing the salt content of the soil around them. What had started as an attempt to find a use for water that seemed to have no use had become something considerably more interesting. A closed system where water drawn from deep underground nourished fish, and fish waste-nourished trees, and trees filtered the water back toward the source. Every element feeds the next, and almost nothing is wasted along the way. Any farming system, no matter how elegant its biology or how clever its engineering, only continues to exist if the numbers work. Good ideas that cannot sustain themselves financially do not last. They become interesting footnotes in academic papers and pilot projects that never scale. The reason the Negev system did scale, and the reason it continues to expand, comes down to a straightforward, economic reality that becomes clear when you compare the cost of water in Israel against the cost of the water being pulled up from the Nubian aquifer. Fresh water in Israel is expensive. The country is small, dry, and heavily dependent on desalination plants that process seawater from the Mediterranean into drinking and irrigation water. That process works, and Israel has become genuinely world-leading in desalination technology, but it is not cheap. Fresh water from desalination costs somewhere in the region of 60 to 70 cents per 35 cubic feet. That sounds manageable until you start applying it to the scale that agriculture actually requires. A single 2.5-acre plot of crops can use up to 88 million gallons of water over the course of a year. Running the numbers on that volume at 70 cents per 35 cubic feet produces a water bill of around $7,000 for a plot that size before any other costs have been considered. Seeds, labor, equipment, pest management, harvesting, transport. None of that is included in the $7,000. That is purely the cost of the water. A typical olive grove generates somewhere between $12,000 and $15,000 per 2.5 acres annually, depending on conditions and market prices. If half of that revenue is consumed by the water cost alone, the profit margin left over is thin enough that almost any unexpected expense, a bad season, a drop in prices, equipment failure, tips the operation into a loss. This is a significant part of the reason why 60% of Israel is desert, but contributes relatively little to the country's conventional agricultural output. The land is there, the sunlight is certainly there, but the economics of irrigating it with desalinated water do not work for most crops. Water from the Nubian aquifer costs almost nothing by comparison. The drilling was a one-time investment made decades ago. The artesian pressure that forces the water to the surface without pumping means that operating costs are minimal. Farmers using aquifer water pay roughly 5 to 10 cents per 35 cubic feet, which represents a discount of around 90% compared to desalinated fresh water. That single factor transforms the financial viability of farming in the region entirely. But the real economic innovation in the Negev system is not just that the water is cheap, it is that the same water gets used twice, and the cost of accessing it gets shared across two separate industries that would otherwise be competing for the same resource. The fish farm pays for the pumping required to bring the water up from depth. It uses that water to raise fish, and in doing so, the water absorbs heat, picks up fish waste, and becomes enriched with nitrogen and other nutrients. At that point, the water leaves the fish operation and moves to the agricultural fields. The crop farmers pay nothing for the water because it is a byproduct of the fish operation rather than a primary purchase. They also pay nothing for fertilizer because the nutrients dissolved in the water from the fish waste serve that function directly. The fish farm benefits because its water cost per unit of fish produced drops to almost zero. The crop farm benefits because two of its largest input costs, water and fertilizer, are effectively eliminated. And the fish farm has no waste disposal costs because the water leaving its ponds has immediate value to a neighboring operation rather than being a liability that requires treatment or careful management. In some arrangements, fish farmers sell or trade their outgoing water to crop farmers, creating an additional revenue stream on top of the fish themselves. Neither industry could sustain itself using these inputs independently. A fish farm purchasing fresh water at standard desalination prices would face operating costs that would make profitable fish production extremely difficult to achieve. An olive farm buying synthetic fertilizer at market rates and irrigating with fresh water at pound sum. Full price would be working with margins too tight to absorb normal agricultural risk. But a fish farm using 90% discounted brackish water alongside an olive farm receiving free irrigation and free organic fertilizer can both operate profitably. The shared cost structure makes both viable where neither would be alone. The result is that the Negev today produces over 3,000 tons of fish per year across multiple operations. Israeli barramundi is exported to European markets, where it appears on supermarket shelves in France, Germany, and the United Kingdom, competing directly with fish sourced from Australia and Southeast Asia. Desert farmed fish sell alongside ocean-caught varieties, and in some cases undercut them on price because the production costs are so much lower. The olives and dates produced alongside the fish are sold both domestically and in international markets. What was once considered economically worthless land is now generating real commercial output across two distinct industries simultaneously. The financial case is compelling on its own, but the environmental implications of the system extend well beyond the balance sheet, and they have attracted attention from researchers and policymakers working on some of the larger questions facing global agriculture. Conventional agriculture is a significant contributor to greenhouse gas emissions. Synthetic fertilizer production, through the Haber-Bosch process alone, emits close to 500 million tons of carbon dioxide annually, accounting for roughly 1% of total global emissions. Transporting that fertilizer from the industrial facilities where it is made to the farms where it is used adds another estimated 100 million tons. Pumping and treating fresh water for irrigation requires substantial amounts of energy at every stage. Taken together, the inputs that conventional farming depends on carry a considerable carbon cost before a single seed has been planted or a single fish has been raised. The Negev system removes itself from most of those costs entirely. There is no synthetic fertilizer, so there are no fertilizer production emissions and no transport emissions associated with it. There is no fresh water being pumped long distances or processed through energy-intensive treatment facilities. The heat required to maintain tropical water temperatures for the fish comes from geothermal energy that exists naturally at depth, which means no gas or electricity is being consumed for heating purposes. Estimates suggest that using geothermal heat rather than conventional heating systems saves the equivalent of around 200 tons of carbon dioxide per 2.5 acres of fish ponds every year. Beyond simply reducing emissions, the system actively removes carbon from the atmosphere. Date palms and olive trees are photosynthesizing continuously, drawing carbon dioxide out of the air and locking it into their wood, roots, and leaves. A mature date palm absorbs roughly 44 pounds of carbon dioxide per year. A mature olive tree sequesters around 66 pounds. A 25-acre plantation containing 1,000 trees removed in the region of 66,000 pounds of carbon from the atmosphere annually, and that carbon remains stored in the living tissue of the trees for decades. When you combine the emissions avoided by eliminating synthetic fertilizer and freshwater infrastructure with the carbon being actively sequestered by the trees growing alongside the fish ponds, the overall carbon balance of the system moves into negative territory. It takes more carbon out of the atmosphere than it puts in. A food production system that reduces its own environmental footprint while generating commercial output is rare enough to be genuinely significant. The closed-loop nature of the system has continued to develop beyond its original design. Some farms in the Negev have begun producing fish feed using algae grown on site in the same brackish water used for the fish ponds, reducing dependence on hards. Fish meal sourced from wild-caught fish. Bottom trawling for fish meal, which is the standard ingredient in conventional aquaculture feed, causes serious damage to seafloor habitats and contributes to the depletion of wild fish populations. Moving toward plant-based and algae-based feed produced within the system itself closes another gap in the loop and reduces the external environmental costs of the operation further. Other countries in the region and beyond have taken notice. Egypt, which sits above a much larger section of the Nubian aquifer than Israel does, has launched pilot fish farming operations using similar principles, drawing on technology and knowledge developed in the Negev. Saudi Arabia, which is in some respects even more water-constrained than Israel, has invested in integrated aquaculture and agriculture projects in desert areas near Riyadh. The underlying logic of the system, using what is available rather than trying to import what is not, is transferable to a wide range of arid environments across the Middle East and North Africa. There is also a broader potential application for one of the system's secondary discoveries. Long-term monitoring of the soil in the irrigated fields around the Negev fish farms found that salt levels remained stable or declined over time, with the olive trees and date palms absorbing salt through their roots and removing it from the soil through the natural leaf drop cycle. Across the Middle East and North Africa, there are millions of acres of farmland that have been damaged or rendered completely unusable by salt accumulation from decades of improper irrigation practices. The same trees that are producing commercial fruit in the Negev could theoretically be used to rehabilitate that land, using brackish water that already exists underground in many of those regions and currently serves no purpose at all. What the Negev story ultimately demonstrates is something that goes beyond fish farming or desert agriculture or water management in isolation. The conditions that made the land appear worthless and in and out, when examined from a different angle, to be the exact conditions that made a particular kind of system not just possible, but uniquely well suited to that location. The heat that disqualified the water for drinking eliminated the single largest operating cost in tropical fish farming. The salt that killed conventional crops filtered out everything except the species that were already built for it. The ammonia that threatened to poison the fish provided the fertilizer that made the trees grow faster than expected. None of those problems disappeared. They were simply reassigned from the category of obstacle to the category of input. That reframing is not specific to deserts or fish or ancient aquifers. It applies anywhere that a fixed set of constraints has been accepted as a permanent limitation, rather than examined as a potential set of starting conditions. As water becomes scarcer in more parts of the world, as soil quality continues to decline in heavily farmed regions, and as the pressure to reduce the carbon footprint of food production increases, the question the Negev asked in the early 2000s becomes more relevant, not less. Not what is missing, but what is already there, and what is it actually good for.